And hello, welcome back. So just the last video we are talking about integrating this skin friction coefficient. Skin friction coefficient. Let's see what we can do to have this integral done properly. Okay, so what's Rex again? We have to substitute back our original equation. So it's actually ux over nu. So we'll have to u infinity x and nu will actually go on top. Alright. Okay, now we can integrate. Actually, this 0.6464 nu u infinity, all of this can be brought out. And this is just a square root integration. Pretty simple. Okay, let's bring out this 0.6464 and put it outside. Okay, nu will also go outside on the numerator, and u infinity will go in the denominator. Okay, so this will be just 1 over square root of x. I'm sorry, I think messed that up again. Square root of nu, square root of u infinity, and x. Yeah, see, careless mistake again. Square root of u infinity and x, and okay, there you go. And again, square root of nu and square root of u infinity. Alright, there you go. Not too much of an issue there. No issue. Okay, so now we will need to do few things. Integrals of 1 over square root x, very simple. In fact, of course, we can use Wolfram. Of course, we can use the x over L kind of a trick, but never mind. I'm not going to do that. Let's just do the standard way, right? Analytically. So we actually have to. Okay, maybe I'll just skip this part. All right. I will just say that the answer is 2L. Okay, 2 times square root of L. Cause I'm a bit lazy. Okay, so when you integrate, you raise the power by 1, then you have a square root of x, and then you divide by the power of that square root, which is half. You divide by half, you get 2. You get 2 square root x being your integral. Then you take definite integral x at L minus the integral evaluated at x equals L minus integral evaluated at x equals to 0. Then you get 2 square root L. Okay, and just roughly explain. I don't want to type that all out, it's very time consuming. So this 2 will go in here, and let's 2 times whatever this is here, 1.2928. Let's put 1.2928. 1.2928. Let's bring this L in. Okay, because just the difference between x and L, I mean conceptually speaking, x is just a point over here, but L, you're kind of measuring this whole length. Okay, I mean pretty much. I mean they are equal in quantity. At x equals to 5, L equals to 5. There's no difference in quantity, but just take note. This one actually is talking about what do you call that? A comprehensive average. I mean it's an average Reynolds number. So okay, I already done the multiplication. Let's take the 2 out, and of course square root L will appear at the bottom, and Therefore, you will get a square root of Reynolds number at the bottom in the denominator here. And that's all we are doing. That's all. Very simple. And you can see the von Karman solution is way easier to work as compared to maybe the similarity solution, because that one you kind of need to work your way around. Whereas for this, you can kind of use just a very simple calculus and some assumptions. You will get your answer. But as for the other one, you probably need a Frobenius method. I mean, you can do the same thing. You can actually compare the results. Okay, so what are the results? Okay, so von Karman. Okay, the von Karman results are as follows: CFL is this, CFX is this, and of course the boundary layer thickness is like that. Okay, this is the approximate solution. All right, and if you want to really make this look nicer, then let's do this then. Let's put this over here. Yeah, this one makes it looks a lot nicer. All right, that's way better. Okay, von Karman results are like so, and if you look at the Blasius results, exact solution. Okay, exact in the sense that you don't make any of these approximations, but depending how you solve the Blasius solution, the similarity solution, of course your results may differ a little bit here and there, depending on your step size and how many terms you use in your series solution. Okay, but in general, Blasius solution is like so. Okay, Blasius solution is like so. Okay. Okay, Blasius solution, you have actually a 5 on top. This is the thickness. And the CFX is 0.664. And I actually just copy these values from the textbook called Fundamentals of Momentum, Heat and Mass Transfer. And now, of course, the average, what do you call it? The average, what do you call it? Skin friction coefficient is like so, 1.328. So it's just basically 2 times. Okay, you notice that it's not that bad an estimate. Okay, even though this von Karman results, the approximate solution is just an estimate, it actually gets pretty close. Okay, 4.64 compared to 5. Okay, you're about less than 10% off. Okay, you're less than 10% off. Okay, if you divide by 5, then times 100. Okay, you're about 7% off, right? Equals 100 minus, yeah, you're actually 7.2% off if you compare this skin friction boundary layer thickness. You're about 10% off, or 7.2% off. Okay, this skin friction coefficient is 0.664. minus this, and you're about you're about 3% off. Yeah, 3% off. So 7.2% off for percent off for BL thickness, and 3% off for skin friction coefficient. That's pretty good. Yeah, it's pretty good. So So the thing is this, this actually shows, that von Karman method is pretty good, even though, okay, yeah, I mean the von Karman method is simpler. You don't think about all the what do you call that, similarity solution, and it's not as exact as the Blasius results. But this so-called comparison of a von Karman compared to Blasius results, which are exact or analytical solution, so to speak, it shows that von Karman method is pretty good. Okay, these approximations is pretty good. These are pretty good. So if you can't use Blasius results, because Blasius results only apply for the flat plate, and von Karman results, this method you can use for flows other than just flat plate flow. Okay, it shows that compared to the real results, I mean we tested it with a flat plate case. And it shows that the von Karman results are good. If it matches for the flat plate case, we can kind of be confident that like let's say for aerofoils, von Karman results are also pretty good in comparing these coefficients as well, so long as the boundary layers are laminar, and that's important. Boundary layers must be laminar and the fluid must be incompressible. Okay, so that means maybe it's good for something like a hydrofoil, meaning to say that if the underwater wing, okay, you can have an underwater wing, maybe von Karman may be quite useful for that. But the point is to show you that you don't always have to go 100% accurate as with Blasius results. You can go with the von Karman results and you'll be totally fine. Okay, so that's the point I'm trying to make, and that's the point that textbooks also they're trying to make. So yeah, so I mean if you're interested, you can actually go and try churning out your Runge-Kutta codes or whatever. Try to churn these results out from your Runge-Kutta codes or some other numerical solver for the Blasius solution. Yeah, you can let me know if you do it well. Yeah, I'm not going to do it for the time being. Alright, so that's all I have. And of course, the third method, you want to use its numerical solutions. I mean, you hardcore just solve the Navier-Stokes equation as it is, and you don't cancel terms or anything. You just let numerical solver solve everything. And that is under computational fluid dynamics, which things like COMSOL, OpenFOAM, they'll be very good for. And that's all I have for you. Hope this is helpful, and I'll see you guys next time. Bye bye.